Okay, this is section 6.2, part 1, multiplying and dividing radical expressions. And just to continue with the pattern of jokes, I have a little one for you now. What does the little mermaid wear? If you said an algebra, you are correct. So we're going to start this section by talking about ways in which we can combine radicals. And the first way is to multiply them. Well, in order to multiply radicals, you have to make sure that they have the same index, or the same root. So on the general rule, we have the nth root of A times the nth root of B. So we can go ahead and combine them as the nth root of A times B. So as long as you have the same index, you multiply the radicands together. Quick example. We have the cube root of 4 times the cube root of 3. Well, since they're both cube roots, we can rewrite this as a cube root of 4 times 3, which we can then simplify as 12. And if 12 can break down, you would want to do that. Okay, so let's go ahead and practice multiplying the radicals. Example 1. We have the cube root of negative 4 times the cube root of 2. And again, since they're both cube roots, you combine them by rewriting them as negative 4 times 2, which is a cube root of negative 8. Now, negative 8 does have a cube root. Remember, this question is asking what value times itself 3 times gives you negative 8. And that answer is negative 2. Example 2. We have the fourth root of 7 times the fifth root of 7. Well, you notice they have the same radicands, and that's great, but if they don't have the same index or the same root, you still cannot multiply them together. So the only thing I can do on this problem is write not possible. Example 3. We have the square root of 48 x to the fifth y squared. Now we're not multiplying anything in this problem, but we do need to simplify it. 48 is not a perfect square, so you want to find a factor of 48 that is a perfect square. So what I do is I start by listing all my factors. Let's see, we have 4 and 12, 5, and then 6 and 8, and I think that's the last pair. Now there are a couple pairs here that have perfect square factors. And the reason I'm choosing perfect squares is because my index is 2. I want to take a square root of a value. 4 times 12 and 3 times 16. You want to choose the pair in which you have the largest perfect square factor. So I'm going to choose 3 and 16. All I do is I simply rewrite 48 as 16 times 3. Now for the x to the fifth, I'm going to rewrite that in groups of 2 because that's, again, my index. So this is going to be x squared times x times x. And you can double check that if you add, because we're multiplying these same bases, we add our exponents. So that's 2 plus 1 more. So we still have x to the fifth. And then of course my y squared. Now I'm going to go ahead and do the square root of each of the factors underneath the radical. And if I cannot do the square root of it, I'm going to circle it. So the square root of 16 is 4. The square root of 3 I cannot do, so that's going to stay under the radical. But I can take the square root of x squared, and that's x. Square root of this x squared is x again. I cannot take the square root of 1x, so that stays inside. And the square root of y squared is y. So I simply rewrite this. Oh, that's it. I'm going to go ahead and combine the outside, and I have 4 x squared y times the square root of 3x. Okay, example 4. We have the square root of 45 x to the fifth y cubed times the square root of 35 x y to the fourth. So I'm doing the square root on both of them, which means I just need to multiply the radicands together underneath one square root. So I have 45 x to the fifth y cubed times 35 x times y to the fourth. And now I go ahead and I can multiply like terms. Well, 45 times 35 is 1,575. X to the fifth times x, because I'm multiplying same bases, I want to add their exponents, so I get x to the sixth. And then I have y cubed times y to the fourth. Well, 3 plus 4 is 7. Now, for your part of your homework tonight, besides watching this video, is to finish this problem. 1,575 is not a perfect square, so you need to break it down into factors that are perfect squares. Good luck! Another way to combine radicals is to divide them. And just like we did with multiplication, we had to make sure that they had the same index. So we do that when we divide as well. We have in the nth root of a divided by the nth root of b. So I can rewrite this as one large radical. It'll be the nth root of a divided by b. Quick example. Let's say we have the square root of 27 divided by the square root of 3. Well, this looks horrible to try to simplify. But because we're doing the square roots for both, I can just rewrite them as the square root of 27 divided by 3. And now I can simplify. Because 27 divided by 3 is 9. So I really have the square root of 9, which we can simplify again and get 3. Alright, so example 1 says to divide the radicals. We have the square root of 50x to the sixth divided by the square root of 2x to the fourth. And since we have square roots in both numerator and the denominator, we can rewrite this problem as one large square root. And the radicand becomes 50x to the sixth divided by 2x to the fourth. And now we can go ahead and divide like terms. Well, 50 over 2, that gives us a square root of 25. And if you notice, we have x to the sixth over x to the fourth. And anytime you're doing division where you have the same basis, we make sure that we subtract our exponents. So we get y squared. And now we can take the square root of each of the inside terms. So the square root of 25 is 5. And the square root of x squared is x. Example 2. Now we have the cube root of 162, y to the fifth, divided by the cube root of 3y squared. So since we're doing cube roots for both of them, we can rewrite this as one large cube root of 162, y to the fifth, divided by 3y squared. And what you want to do then is simplify the radicands. 162 divided by 3 is 54. So I'm going to rewrite this as a cube root of 54. Y to the fifth divided by y squared becomes y cubed. 5 minus 2. And now I want to go ahead and simplify the radicands again. But 54 itself is not a perfect cube, so you need to find factors of 54 that are. And if you said, oh, well 27 times 2 is 54, and 27 is a perfect cube, you are correct, because that's a pair that we want to use. So the cube root of 27 is 3. I cannot take the cube root of 2, and the cube root of y cubed is y. So this becomes 3y times the cube root of 2.